So welcome back to Calc 2. This is our video on 8.5 partial fractions. So you may recall from pre-Calc 2, you worked with decomposition of rational functions using partial fractions. So what is that exactly? Let's start with, if I have 3x over x squared plus 2x minus 8, I can break that down into 1 over x minus 2 plus 2 over x plus 4. All right, so how does that work? Well, first, let's start with this piece. And let's confirm that it actually does work. You know how to add rational expressions. We add rational expressions by using a common denominator. So I'm going to leave some space. Since my denominators cannot be factored, cannot be broken down into other factors, our common denominator ends up being, right, x minus 2, x plus 4. To know how to break down a fraction, you first have to recall how to pull it back together. So how do I do that? Well, I would multiply. I have my x minus 2 here. I need my x plus 4, right? I've got the x plus 4 on this one. I need x minus 2. And this is just a quick review of intermediate algebra in this case. Then we have, I work it out, x plus 4 times 1 is x plus 4 plus 2x minus 4 all over x minus 2, x plus 4. So that would give me 3x x squared plus 2x minus 8. So this is what you first learned how to do back in algebra. You take two rational expressions and bring them together into one rational expression through addition or subtraction. Then along the way in pre-calculus, you learned, well, how do I take my 3x over x squared plus 2x minus 8 and break it into these two partial fractions? So let's review that process real quick, and then we'll understand why we need it. So again, I'm going to write down the original. And let's review the basic process of putting our taking a rational expression and breaking it into partial fractions. Start by coming up with what we call the partial decomposition of our original fraction. And we say, okay, 3x over x squared plus 2x minus 8. Well, first of all, if I can factor it, it certainly makes it much easier. So it's x minus 2, x plus 4. So we already can determine we're going to have an x minus 2 and an x plus 4 by putting the factors down. And then we're going to have something over x minus 2 plus something over x plus 4. What we need to figure out is what those somethings are. This part is the part here is called the partial decomposition. Okay. And by kind of going through these steps backwards, well, we know that this is going to equal, this 3x has to equal some combination because of to get the common denominator of a times x plus 4 plus b times x minus 2. All right, so I can work that out. That's ax plus 4a plus bx minus 2b. What I want to do at this point is rearrange my a's and b's together. So ax plus bx plus 4a minus 2b. My ax, you can combine ax plus bx. It ends up being a plus b, whatever that is. X is the coefficient of x. Then you have a 4a minus 2b. So we're going to group our terms together that don't have an x in it. And then we're going to group, so this is our coefficient of x. These are our constant. Okay? And as you can imagine, if we get into terms with higher degrees, we're going to have a coefficient of x squared, a coefficient of x, and then a constant. So come back over here. Well, I only have 3x. But isn't this also 3x? What's my constant on this term? My constant happens to be 0 because there's nothing there. If it was plus 5, your constant would be 5. So here, 3 is our coefficient of x, right? And this is our constant. So what do we do with all this information? We can set up a system of equations. Very simple system of equations. So my coefficient of 3, well, a plus b have to come together to equal 3. And now we know that 4a minus 2b has to come together to equal 0. And we have a basic system. That we can solve. So I'm going to solve this system very quickly. You all know how to solve a system. Notice I have a negative 2b, so if I can get a 2b there by multiplying by 2, it'll cancel, which I got to turn that and then make that a 6. So I can multiply the whole top term by 2. That gives me 6 equals 6a and 0. So a equals 1. And then I can just substitute into any equation. So we know a plus b equals 3. B equals 2. What that lets me do then is to rewrite my partial decomposition with my a and b. So what we know now is that my 3x over x squared plus 2x minus 8 is 1, go back to the top, over x minus 2 plus 2 over x plus 4. So how does this help us with integrals? I'm going to show you how it helps you with integrals. If I asked you to integrate 3x over x squared plus 2x minus 8 dx, you might try u sub and say, okay, u equals x squared plus 2x minus 8. du is 2x plus 2 dx. There's no way you can get a 2x plus 2 from a 3x. You can get the 2 by multiplying by 2/3, and then multiplying out here by 3/2. That part's fine. But you can't add a 2 and subtract a 2 to balance it out. Doesn't work with a u sub. So u sub does not work on this particular problem. Or if it does, it gets much more complicated. If you recall, there was one in 8.1 where we it did a whole bunch of work to solve an integral. This one's a little bit more straightforward. By breaking it up, I now have the integral of 1 over x minus 2, right? And we can even separate it into two integrals over the integral of 2 over x plus 4. Why is that helpful? Because now, when my u equals x minus 2, my du is simply, 1 dx. Even in this one, if u is x plus 4, du is 1 dx. So I can integrate them each separately. This one works out perfect to the integral of du over dx. For this one, you need a 1 in the denominator, so you have to actually multiply by 1/2, and you got to get my 1, which means I need to balance that out with a 2 out front. So you just got to be careful there. We didn't need to do it in the first integral, but we do on the second one. And then it is over du. I don't know why I wrote dx. That's u. Sorry about that. U. So the integral of 1 over u is ln. Remember, this is the u from the first. I should have used a different variable from the first one, so it's ln of x minus 2 plus 2 ln of x plus 4. And you can actually pull that one together using your ln properties. If you have multiple ln's like this, this is plus, so you multiply them together. X minus 2 times x plus 4 squared. Don't forget your plus c. All right, so taking your rational expression and decomposing it into partial fractions is a way to help you integrate better. The hardest part here is probably doing that decomposition into multiple fractions. So just to help you out, there are some cases that you've learned. That one was very basic, but we have what we call partial fraction decomposition cases. So obviously and it really just comes down to your factors, right? So if your original is over something where you can factor into x plus, you know what, we'll use m and n, something x plus n, then you have, one term, right? Just as the one we just did. Right? Now here's a tricky one. If your denominator is, it doesn't matter if it's plus or minus, and it's squared, right? Here's where you got to be real careful, because it's not x minus c and x minus c, or x, doesn't matter if it's plus, x plus c, x plus c. In order to get a squared, one of them is to the first power, and the second one is to the second power. So be careful. That one's a tricky one. All right. And so on and so on. If you had something where you had an x and an x plus m, x plus n, every single one of them is going to be over, right? And here you're going to have 3 terms. So it really does come down to all of the different factors in the denominator. Just again, be careful here. To the first power, oops, and then to the second power. So let's try some examples. Okay, so let's do, oops, sorry. Integral x squared plus 2 over x cubed minus 2x squared plus x dx. So again, when you're looking at this integral, your first thought is, can I do a u sub? And, you know, looking at the denominator, okay, I have the x squared, but I need 3x squared minus 4x plus 1. I don't have the x term. I don't have the right terms here. So you cannot use that u sub because you cannot get that kind of perfect derivative of u if you let u be that denominator. Once you get to that point and you see this rational expression, it clearly isn't even going to fall into one of our, it's not a trig sub because you've got a trinomial. That's where you're going to kind of left with at this point, trying that partial decomposition of your fraction. So let's just take our fraction out of the integral. And as I do that, I'm going to factor the denominator, right? So I'm going to pull out that x. And when I pull out the x, I'm left with, what is that? X squared minus 2x plus 1. But isn't x squared minus 2x plus 1 is also factorable, right? And it's x minus 1 squared. All right. So here's a kind of cool thing to think about. My initial highest exponent in the denominator was a cube, so I should have 3 decompositions here. My first one is just over x. Now remember what I said. When you have a binomial squared, you really have an x minus 1 and another x minus 1. So the second one is over that binomial to the first power. And then your third one is over that binomial, to the second power. All right. I'm going to do the decomposition out of the integral, and then we'll put it back in. So now I have to think about this fraction over here, the a over x plus b over x minus 1 plus c over x minus 1 squared. What would I need to multiply the first term to get my common denominator? Well, my common denominator, obviously you have it right here, is going to be x minus 1 squared, right? X. Well, I have the x. What do I need? I need the x minus 1 squared over x minus 1 squared. So that's what I need for the first term. What do I need for the second term? I have one of my x minus 1s. I don't have the x, and then I need another x minus 1. I'm trying to get each of these denominators to come out to that initial denominator of x minus 1 squared. I have the x minus 1 squared. Now I need x over x. All right, so let's bring all this together. What is that going to give me? I'm going to combine it, and then I'm going to go ahead and put it in one term. So if you want to off to the side, what is x minus 1 squared? That's your x squared minus 2x plus 1. All right. So for the first term, I need a, right? I need a times x squared minus 2x plus 1. I'm just trying to save some work of constantly having to rewrite this a whole bunch of times. I'm going to distribute the a. It's going to give me ax squared minus 2ax plus a. All right, for b, what's that going to give me? X squared minus x times b. So it's bx squared minus bx plus cx. All over my denominator squared. Okay? Now remember how we grouped it. You want to group your squares together, your x's together, and your constants together. All right? And you don't have to necessarily go through all these steps, but I'm going to show them to help you. So for my x squares, well, I have an a plus b x squared, right? Because I have ax squared. Bx squared is going to be a plus bx squared. All right. For my x's, I have a negative 2ax minus a bx plus a c. So that's going to give me, I'll do plus negative 2 a minus b plus c for my x. And then my constants, I just have an a. So what terms only don't have a variable? Just that one. All right? So plus a. So I regrouped everything. So I had my x squares and all the coefficients of those added up, my x and all the coefficients of that one added up, and then my a by itself. All right, that allows me to set up the systems of equations. So how is that system going to work? Well, come back, I have an x squared, right? It's x squared plus 2 is my initial numerator. What's the x term? There is no x term, so that's going to be 0 plus 2. So when I set up my system, my x squared has to match my x squared. So for my x squared terms, well, that's a 1. 1 equals a plus b. For my x terms, that's a 0 equals negative 2a minus b, minus b plus c. And for my constant, well, that's a 2. 2 equals a. Now that's the system that I need to use. This one, use whatever method you need to solve the system. This one's pretty straightforward. You learned solving multiple equation systems in algebra and in pre-calc. Sometimes if you have an A, B, C in all three equations, you got to pick two, eliminate one variable, match it, pick two more, eliminate the same variable, and bring them together. So there's a lot of different methods here. This one's pretty straightforward because we already know, hey, A is 2. Well, since I know A is 2, I can pop A up there. Right? So 1 equals 2 plus B. So then B, right, is negative 1. Once I have A and B, I can just plug it into that third equation. It says negative. It says 0 equals negative 2 times A minus B plus C, because I just need to get C now. So that comes out to -3, so 3 equals C. All right. I now have my A, B, C. I can now go plug that back into my integral by using the, whoops, that's not what I wanted to do. Hold on. Doesn't want to cooperate with me right now. There we go. By using this one, and this one. All right. So what's that going to give me? I'm going to integrate 2 over x minus 1 over x minus 1, because b was -1, so we're going to move the 1 there, plus 3 over x minus 1 squared. I have to do a lot of individual u sub. The first two are pretty straightforward. Hopefully you recognize. Bring the 2 out, it's just 1 over x, right? So that's just going to be the integral of 2 ln of x. Same for this one, because the derivative is just 1, so it's minus ln of x minus 1. This one's a little more, you got to do a quick u sub here. Let u equal x minus 1. Du equals 1 dx. So your integral, so you just take it off to the side. Your integral, I need a 1, I have a 3. So to make that a 1, I have to multiply by a third, which means you're going to multiply the outside by 3. 3 ends up being 1 over u squared du, which gives you 3 u to the -1. So when you put it back in, it's 3 over, because it's 3 times 1, so we'll put the 3 back up here, over x minus 1, because when you plug in your x minus 1, it's to the -1 power, so that means it just moves to the denominator. Plus c. These two ln's can go together. This actually becomes ln of x squared. Minus that becomes ln of x squared over x minus 1 plus 3 over x minus 1 plus c. Okay. Let's take a look at another one. So again, I'll pop this one up. Try it on your own. The rest of this video, I'm just going to go through a couple different examples. So for each one, just practice on your own, then come back to the video and watch it get done, or scroll to the end and see that you have it. All right. For this example, I'm going to take x squared plus 12x minus 4 over x cubed minus 4x dx. All right, so first thing I like to do is I'm going to take my denominator over here and really factor it out. So what do we get? We get x squared minus 4. Oh, so I have x minus 2, x plus 2. So we have 3. So we're going to have another ABC problem here, right? So my integral would end up being a over x plus b over x minus 2 plus c over x plus 2 dx. So let me quickly go through the partial fraction decomposition. I'm going to take it out of the integral to do that, and then we'll put it back in the integral. So clearly my first term needs to be multiplied by x squared minus 4. And x squared minus 4 is, right, times a. So that's going to be a times x squared minus 4, because it's a times x minus 2 times x plus 2. So that's going to give me ax squared minus 4a. Second term, I need the x plus 2 times the x, so x squared plus 2x. So b x squared plus b 2x, or 2bx, however you want to, it should be 2bx. Let's do it that way. And the last one's going to be, of course, x times x minus 2, x squared minus 2x multiplied by c. So it's c x squared minus 2c x. Okay? Again, if you want, you can skip this step, but if you want, you can put everything together. There's my squares. So you don't have to write it out this way. You can jump right into your, here, we'll jump right into the equation, keeping in mind what it has to equal. So what is the coefficient in the original problem of x squared? The coefficient is 1. So that means a plus b plus c, for my x squared terms, a plus b plus c equals 1. So there's my first equation. Do the next one in blue. So let's just look at our non-squared values, our x values. So I have negative 4a, that's a constant. Hold on. I need my x. There's one. 2bx and 2cx. They are my only x terms. Yep. So that, you can see, has to come out, that coefficient has to come out to 12. So for my x terms, I have 2b, sorry, don't include the x, minus 2c has to equal 12. And for my last one, the constant, I only have a negative 4a, right? I don't have anything else, any other term that has no x in it. So that one simply becomes, for my constant, negative 4a equals, what was that? Negative 4. Okay. So there's my equations. Remember, when you set up these 3 examples, they do not have x's in the equation. You're only looking at the coefficients of x squared, the coefficients of x, and your constants. And they have to match these. So the coefficients of x squared have to equal 1. The coefficients of x's have to come together to get 12. And the constants come together to make negative 4. This one works out real nice again. You just go ahead and plug that into there. Obviously, a equals 1. So now I have in that first equation, that green equation, it actually becomes what? B plus c equals 0, correct? Yeah. Because I have 1 plus b plus c equals 1, so b plus c equals 0. And then I also know that 2b minus 2c equals 12. So remember, you're trying to find a combination. 2 equations, 2 unknowns. If you have 2 equations, 2 unknowns, then we can go ahead and solve this. I would multiply the top equation by 2, right, by 2, making it 2b plus 2c equals 0. My blue equation is 2b minus 2c equals 12. And when I go ahead and add them up, I get 4b equals 12. So b comes out to 3. So we know a is 1, we know b is 3. It looks like c would have to be negative 3. So you can do it anyway. You can put the b into the blue equation. That's 6. 12 minus 6 is 6. Divided by negative 2 is negative 3. So yes, C is going to equal -3. All right. So A is 1, B is 3, C is -3. And we're going to go ahead and plug it into our original integral. Breaking up those fractions is going to give us A is 1, so it's 1 over x. B is 3, so 3 over x minus 2. Minus, because that numerator, that C is negative value, minus 3 over x plus 2. And then you go ahead and integrate. This is going to, I'm going to skip all the integration steps. You know how to do the UN. It's going to be a lot of ln's. You know how to do the u sub. It's going to be a lot of ln's in this one. So it actually ends up being ln of x plus 3 ln of x minus 2 minus 3 ln of x plus 2. And yes, you can bring all those ln's together. The first two get multiplied and then divided by the third, but be careful with your coefficients. Please pull them. I mean, your coefficients of your ln's, you're multiplying by 3. Pull them as exponents. So when you rewrite it, you end up getting x times x minus 2 cubed over x plus 2 cubed. That's using all of your properties of exponents. And there's your answer. So again, we're going to go through a couple more examples. A couple things I just want to note real quick. Suppose we had x squared plus 1 over x to the 4th minus 4x cubed minus 32x squared. Clearly you would start to factor that, right? So this one is okay because you pull out an x squared and then you're left with something you can actually factor. Right? So you have x squared. So that's going to be minus 8 plus 4, I believe. Yeah. So when you do the decomposition on this one, I also want you to note that this too is a repeated. When you have, it works just like when we had x minus 1 squared or x plus 2 squared or anything like that. In other words, you have to use the two different. You've got to put a over x. You got to use the x and the x squared. So when you go to integrate it and you go to find, before you can integrate, and you go to find your A, B, C, and D terms, it's not that it's that difficult, but you do, please make sure you remember to do A, X, and X squared separately. You know, we're not going to do an integral on this, but I do want you to recall how to do the fraction. It gets a little messy because we have to multiply and you're going to get a lot of terms. But so we're not going to actually go through the whole problem, but do make sure if you have an x and an x squared, you've got to write them separately. But what happens when it doesn't factor? So that was the other one I wanted to look at. Let me find one I like. All right, I'm just going to take one of these. Okay, so now let's do one where it doesn't factor. So this one has a lot going on, but we'll you get through it. So I'll write the denominator in already factored form. So you don't have to worry so much about your numerator. That's just going to tell you what your coefficient of x squared should be, your coefficient of x, and your constant should equal. What we need to concern ourselves with is that denominator, because that denominator does not factor. You cannot factor x squared minus 2x plus 3. So how does this work? Well, in this case, your 7x squared minus 13x plus 13 over so your first factor's fine, x minus 2. But notice your second factor is an x squared term. So when we have an x term, we don't have an x in the numerator. It's if this is x to the first, then the x up here is technically x to the 0, so we don't write it. So what that means is if our factor is an x squared term, then we need an x term. So we have an a, we're still going to have a b and a c. So we write that as a, sorry, it doesn't want to work, bx plus c. Okay, you have a quadratic, you need a linear. So think of it this way. When you have a linear, that's what linear is, this to the first power, then you just need a constant. If you have a quadratic, you need a linear above it. All right. How do we write a linear? Well, think of a linear equation, bx plus c. You need the x term, coefficient plus a constant. Here we just had a constant. So keep that in mind if you have something like an x squared in your denominator. So we can go ahead and work that out. Obviously, we need the x squared minus 2x plus 3 for the first term, so that has to be multiplied through by a, right? Ax squared minus 2ax plus 3a. So you've got to do a little bit more work on this one because we have to now take and multiply that by x minus 2. So what is that going to look like? Well, bx times x is bx squared, bx minus, so minus 2bx plus cx minus 2c. The process doesn't change, just gets slightly more complicated, I guess. Bx squared minus 2bx cx minus 2c all over but we're concerned with getting it all together. If we want to go ahead and group it, you can group it or we can just look at it this way. What are all my x squares? There's an x squared. I'm going to underline them in green. There's an x squared. So, can we say that a plus b has to equal 7? Because the coefficients of the x squareds have to come to 7x squared. So for my x squared terms, right, 7 equals a plus b. All right, now let's look for my x terms. There's an x term. And it looks like for this one, for my x terms, not squared, right? I needed to equal negative 13, and that is negative 2a minus 2b plus c equals negative 13. And for my final, my constant, where is it? 3a minus 2c. Yep. For my constant, which is a 13, that is 3a plus c. No, minus 2c, sorry. So I have my equations. And you can solve the system any way you want. If you want to throw a matrix in your calculator, you can. Of course, you can't do that on the test, but you can solve the system using your substitution, using whatever you want. So I'm looking at this, and I think what I want to do is take this equation and this equation, eliminate the c's. That'll give me a nice AB equation I can combine with number 1. So that's what I'm going to do. Again, there's so many different ways you can do it. Find a quicker way. However you want to do it. For me to combine the two equations I highlighted, I need to multiply the top one by 2, because that'll give me a 2c, because remember I said I want to eliminate c's. If I eliminate c's, I can combine it with the first equation, which just has a's and b's in it. So I got to double it. So this becomes negative 26 equals 4a minus 4b plus 2c. And then I can just copy this equation over. And this is just solving multiple systems. 3a, line everything up. I don't have a b in that equation. So that's going to give me negative 13 equals negative a minus 4b. C's cancel. So then I can use that negative 13, that new equation I created, really nicely with the first equation in green, because by adding them together, my a's will automatically cancel. And so that's going to give me what? Negative 6 equals negative 3b, so b equals 2. Yep, b is 2. If I know b is 2, I can see real quick from that first equation that a has to equal 5. And then by plugging in my 2 and 5, I can see that c is 1. So there you go. I got everything, which lets me now go back to my integral. Remember how this one was set up. First, a over x minus 2. So 5. And I'm going to make them separate integrals. It'll be a little easier to integrate then. But my second one is bx plus c over the x squared minus 2x plus 3. So bx plus c over x squared . So you have two integrals that you can integrate separately. The first one is a little bit easier because you can bring the 5 out. It becomes a basic natural log. That one, if you integrate down, actually is just ln of 5 ln of x minus 2. All right. This one a little bit more complicated, but I have 2x sorry, I put c there. It's supposed to be 1. Now, here you're going to run into a little bit of issue again, right? Because if you let u equal 2x minus 2x plus 3, du has to be 2x minus 2. I don't have 2x minus 2. I have 2x plus 1. Well, it would be great if I had 2x minus 2, but I don't have 2x minus 2. So we actually can split an integral. This is another algebraic technique. And say, okay, I need 2x minus 2. All right, but I have 2x plus 1. So if I make it 2x minus 2, I do have to add something to get it back to plus 1. I'd have to add a 3. I didn't really change my integral because what is minus? I just took 1 and changed 1 to minus 2 plus 3. I didn't add anything. I didn't change anything. Like, well, how does that let me do that? Hold on. Okay. I can put this grouping over it plus 3 over the integral. Okay, this particular problem uses a lot. This goes back to we did a problem similar to this in 8.1 where we ended up having to use a tan inverse function, and that's what's going to end up happening here. All right, so we'll forget that first part for a minute and just concentrate on this integral for a second. So, you know, the 2x minus 2 part's fine, right? That integral's great. We can now use u sub on that one. In fact, let's finish that one off. I can use u sub real nice, and it just becomes an ln, and that one becomes ln of x squared minus 2x plus 3 after I use u sub. So this is what I have for the first parts. It's this second piece. This piece where I have the plus 3, so I can go ahead. You create another integral where you just have 3 over x squared minus 2x plus 3 dx. You know, don't worry about, oh my gosh, what's going to be on the test, because there's only limited time on a test. So, you know, it's almost looking like I can give you one integral problem that uses a lot that we learned in this whole chapter, but I will not do that. I'll piece it up into ones that are a little more manageable. But you might get one like this in, say, your math lab or something like that. We did one like this back in 8.3 where we complete the square. I'm not going to go through it right now. If you complete the square, you turn this into x squared minus 2x. You take half of 2, you get negative 1, you square it, plus 2, which is then x. I mean, yeah, half of 1, square it, plus 1, not plus 2. I don't know why I said plus 2. So in other words, you forget the 3 for a second, complete the square on x squared minus 2x. So that becomes x, take negative 2, cut it in half, you get negative 1, you square that, you get plus 1. So it becomes x minus 1 squared. Okay, but I had to add 1. So now I got to subtract 1 from the 3, and that becomes a 2. That just goes back to completing the square method. So then it becomes just an inverse tan. So it's utilizing the idea that the integral of 1 over x squared plus 1, or plus anything squared. Yeah. So we'll put this in A here. This was our inverse tan, and that particular integral, instead of having a 1, we can make it general to make it an A squared. Sorry, A squared. Ends up being 1 over A tan inverse of x over A plus C. So we can actually utilize that for this problem, because the 3 can just come out, right? Don't worry about the 3. The 3 just comes out of the integral. A is 2, right? Or A squared, sorry. A squared is 2. And the x is actually x minus 1. So 1 over A is the square root of 2. Radical. Tan inverse, sorry. And instead of x, it's actually x minus 1 over my A again, which is radical 2. So this tan inverse one does come up a lot, so you might want to kind of get that one down. I'm going to bring these two together and do ln. It ends up being x minus 2 to the 5th plus 3 radical times tan inverse. Not a pretty one, but in case you come across it in MATLAB. There. It is. One more type I need to show you here. So everything we've done so far, in fact, I'm going to scroll up on my screen for a second, have been what we call proper rational expressions. So what does that mean? If you take a look at this one, the highest exponent, if you did x times x squared, is x cubed, so you have an x2 on top. The exponent in the numerator is smaller than the exponent in the denominator. It's a proper fraction, right? Like 3/4 is a proper fraction. If your exponent's smaller than the one denominator, you have a proper rational expression. But if I write one that has the exponent higher, such as x to the 4th plus 1 over x cubed plus 9x, this is what we call an improper rational expression, kind of like the fraction 5/3 is an improper fraction. You can't do the partial decomposition on improper rational expressions. You cannot use u sub on this. You're kind of stuck. But we can go back to long division, right? Long division simply says I take x to the 4th plus 1 divide by x cubed plus 9x. First term into first term. Now there's a lot of missing terms here, but that's okay. We can do it very quickly because we only need to get it down to 1. You know, technically you could sit and do, I need an x cubed, remember this? It's not going to make a difference in this particular problem, so we can just go ahead and actually do a quick long division with it. It's only going to be an x value, right? X to the 4th plus 9x squared. When you subtract, it's going to give me a negative 9x squared plus 1. And you just put minus, right? I can pull the negative out front and make that 9x squared minus 1, just playing with my negative, over x cubed plus 9x. So I can use long division to turn it into something that does have a proper rational expression in it. Because now I have 9x squared minus 1 over x cubed plus 9x dx. I know, it's not pleasant, but it wasn't that bad. And if you need to, you can put in all your zeros and your x to the third, x to the second. It's going to come out exactly the same. Well, the first part's nice and easy to integrate. We'll come back to that. Let's just play with that partial and proper fraction real quick and figure out what we have here. So I'm going to write 9x squared minus 1 over x cubed. Let's factor it, make it a little bit better. Okay. So, well, my first one's easy, just a over x. So my second one is an x squared. Remember what I said? If you have a quadratic on the bottom, you need a linear on the top, so that's your bx plus c. So what's that going to give me? Ax squared plus a9 plus bx squared plus cx. This one's not that bad. The long division was the hardest part of it, it appears. Yeah. Bx squared. Okay. When we solve the system, it might get a little more complicated. Make sure I have this right. Ax squared plus, let me write 9a. That my 9 looked like a D. I don't know why. Plus bx squared plus cx has to equal 9x squared plus 1. So what are my equations? Let's start with our x squared. That and that. So that's easy. A plus b equals 9. For x's, I got 1x, right? C. But I have nothing here, nothing here, no x term. So that just equals 0. And then, of course, my constant is 9a. A equals -1. (9a). Forgot the 9. That's going to make it a little bit more difficult. So that means a equals -1/9. So you got to plug a into the equation. So b actually equals 9 plus a 9th. So 9 to the 9th is actually 82 ninths. So started off a little messy because of the long division. This part was not too difficult, but now we have to deal with these fractions when we plug it back in. So let's get our integral back here. Remember, it started with an x. Okay, minus, because that was our original integral, is x minus. So we have to put a minus there, put it in parentheses, or I can, yeah, let's just put it in parentheses for now. So a is -1/9 over x. And bx plus c and we have 82 ninths x plus c, but plus c is 0 over x squared plus 9. Yep. Dx. Well, dx would be around that whole thing. All right, let's clean this up a little bit. it gives us the integral of x plus 1/9 over x minus 82/9 x over x squared plus 9 dx. All right, we can integrate each of these fairly simply. So the first one is just x squared over 2. That's going to be, you've seen this pattern by now, 1/9 ln of x. I'm going to integrate this one separately, so I'm going to leave the integral sign. I'm going to pull out the 82/9, so we don't have to deal with that, right? And we have x over x squared plus 9 dx. So a quick little u sub is going to give me let u equal x squared plus 9 du equal 2x dx, which means I need a 2, and I need to multiply that by half. Okay. And then that would end up giving me, what, the integral of 1 over u. Yep, so we just have another ln here. We have x squared over 2 plus 1/9 ln of x minus, what's that, 41/9 ln of x squared plus 9 plus c. And you can pull them together. I don't know that it's really going to make it any neater because of the crazy exponents you would end up with. Okay, so we can just leave it like that. Right, so yes, I apologize, another really long video, but I just think it's important to go through quite a few different types of examples so we can hit the different types of fractions, partial fractions that we could decompose in these problems. Okay, that's it for this one.